Well, hey folks, you've been doing it now for weeks, and you probably didn't even know you were doing it. You know what you've been doing? You've been doing the derivative at a point. Awesome, but it's been hidden to you, veiled. And now,
the derivative unveiled.
All right, folks. Well, we did a little coaching on those. Some big words, right? Okay, look with me over here. This is going to be our scenario. Straight line motion. Remember, in calculus, at your level, you can only have straight line motion. Up and down, left and right. In this case, we're going to have a spaceship flying through space in a straight line. It can go forward, it can go backwards, that's it. So S of t equals t squared plus 3. Models the position of a spacecraft traveling in a straight line. In this case, time will be measured in minutes and position will be measured in hours. All right, if I asked you to calculate the average velocity of this ship over a time interval, can you do that? Of course you can. We're using the what? The difference quotient. All right, so the average velocity on time 0 to 5, s of 5 minus s of 0 over 5 minus 0. You only need 2 points to calculate an average velocity. Here's 1 point, 0, s of 0. Here's a second point, 5, s of 5. Just like you always ever needed 2 points to calculate the slope of anything. All right, so what does s of 5 mean? It means plug 5 into this function. S of 0 means plug 0 to this function. You do that and you find out you have 25 over 5 or 5. 5 what? 5 donkeys? No, 5 miles per hour, because this thing is measured in miles and hours, and clearly velocity is miles per hour. All right. What if I asked you to get the instantaneous velocity at time t equals 5 hours? See, when we talk about average velocity, we talk about a velocity over an interval. We're talking about instantaneous velocity, we're talking about a velocity at a particular time. In truth, the concept is exactly the same. Here we use 2 points and solve a difference quotient. Here we use 2 points, in this case 5 s of 5 t s of t, and solve a difference quotient. The only thing is, over here, these 2 points are spread out from 0 to 5 hours. But over here, they're basically going to be at 5 s of 5 and as close to 5 s of 5 as you can get. And the way we make this t s of t infinitely close to 5 s of 5 is by driving t infinitely close to 5. So by sticking this limit in front of this difference quotient, I still have 2 points, 1 and 2. I can still get a slope between those 2 points, right? But that slope is now, might as well be at exactly instantaneously at one particular time, because these 2 points are infinitely close. So let's get the notation going on, because this is derivative at a point. Instantaneous velocity at time t equals 5 hours means, or this is the notation we can use. Commonly in science, v of 5. What does that mean? It means the instantaneous velocity at time 5. In calculus, there were 2 guys, Newton and Leibniz, and they were both discovering calculus about the same time and writing about calculus at the same time. They had different notations because they were different humans. Newton liked this notation, s prime of 5. Say that, s prime of 5. Okay, this is not s1 of 5. There's no 1 there at all. It's a apostrophe or a slash or something like that. It's just a line like that, vertical. S prime of 5. If this said s to the first of 5, that would make no sense, right? We would never see that. And if this was s to the negative 1 of 5, that wouldn't have anything to do with derivatives. That would be in the inverse of s of 5, right? S inverse. But if we see s with this little mark here, that means s prime of 5, and it's telling you take the derivative of s at 5. And really what we've been doing when we calculate instantaneous velocity, the limit of a difference quotient, is taking the derivative of the original function here, s, at a particular point, 5. Leibniz would use this notation, dy dt, where t equals 5. Or he might have used ds dt, where t equals 5. That's probably even more accurate, so let's go ahead and change that. ds dt, where t equals 5. What is velocity, if nothing else but the rate of change of position with respect to time, when at time 5. This is very explicit notation, Leibniz is. That's what your calculator uses, right? When you put in and try to get an instantaneous slope, it uses that. All right, so how do we calculate this? the limit of the difference quotient. 5s of 5, ts of t, drive t infinitely close to 5. These points come together, you still get a slope. You get an instantaneous slope where at t equals 5. All right, well, what does s of t mean? Well, it was given right up here, right? S of t equals t squared plus 3. So just plug in for s of t, t squared plus 3. What's s of 5 mean? It means stick 5 into the s function. Stick 5 into the s function. And just leave t minus 5 as t minus 5. Okay, well, at first you're like, I don't know how this is going to work out. Well, here's what it works out to. 3 minus 3, and then negative 25. So you get limit as t approaches 5 of t squared minus 25 over t minus 5. Hey, that's a difference of perfect squares. So that's t minus 5 plus t. Sorry, t minus 5, t plus 5. T minus 5's cancel, you're left with t plus 5. You get the limit as t approaches 5 of t plus 5. What do? You plug in 5, and what do you get? 10. What are the units for rate of change of position with respect to time? What are the units for? Velocity, which is the change of position with respect to time. Miles per hour. Okay, so this is what we are doing this week. We're going to talk all about the derivative. So this is the instantaneous velocity at time t equals 5 hours. It is the derivative of s at time 5. How do you read it? Velocity at time 5. S prime of 5, which means the derivative of s at 5. ds dt when t equals 5, which means the derivative of s at 5. Use the limit of a difference quotient. Works every time. Another child.
Another example.
All right, folks, so we need another example. That's the best way to just get our head around this. So in this case, we don't have any context like position and velocity. Instead, we just have a function f. So we could talk about its slope, both its average slope and its instantaneous slope. That's all we're going to do. So what type of function is f? A reciprocal function. You know what its graph looks like, right? Looks like this and like that. You've known this for a long time. So f of x equals 5 over x. How am I going to calculate its average slope on the interval from 5 to 10? Difference quotient. F of 10 minus f of 5 over 10 minus 5. What's f of 10 mean? It means stick 10 into the f function. So let's do that. And you get out 5 over 10 or 1/2. And then you stick in 5 and you get 5 over 5, which is 1. 1/2 minus 1 over 5. It's negative 1/2 over 5, or negative 1/10. That is the average slope of this function over the interval from 5 to 10. But what if I wanted the instantaneous slope of the function at, say, time t equals 5? The instantaneous slope at time t equals 5. First, what notation could I use for that? The derivative notation. F prime of 5, which means the instantaneous slope of f at 5, or the derivative of f at 5. Or we can use this notation, which is Leibniz. df dx, like the rate of change of f with respect to x. Or the slope of f at x equals 5. This is the derivative of f at x equals 5. All right. Great. So what are you going to use? The difference quotient. And you're going to put a limit in front of it. The limit as x approaches 5 of f of x minus f of 5 over x minus 5. You know that now. Great. So what's f of x going to equal? Well, we'll give it right up here, this reciprocal function 5 over x. What's f of 5 equal to? Stick 5 into that function. And you get this guy right here. Now, whenever you've got a numerator, denominator in the numerator, and then a denominator in the denominator, you want to collapse this down to just a numerator and denominator, hopefully. So how you can do that? Well, combine like bases. You know, like base over here would be 5x, so you get 25 minus 5x over 5x. But of course, you can see in the numerator here, there's a 5 that factors out, right? So if you factor out that 5, these 5's cancel, and you're left with 5 minus x over x in the numerator. In the denominator, you're left with x minus 5. All right, no problem. 5 minus x is the same as negative x minus 5, right? I'm sure you know that. And then what can I do? Well, I can multiply this right here, which I'll call the numerator, by x. And I can then, whatever I do in the numerator, I have to do in the denominator. So multiply this by x and that by x. And so what happens? This x goes away, and you add an x right here. Well, x minus 5 over x minus 5 are going to cancel, and you get the limit as x approaches 5 of negative 1 over x. What do I do with this limit? Stick 5 in for x, and I get negative 1/5. That is the instantaneous slope of f at t equals 5. This right here, negative 1/5, is f prime of 5. It is the derivative of f at 5. It is df dx when x equals 5, the derivative of f at 5, and it is negative 1/5.
Last example. Live here.
All right, folks, here's yet another example. This is the function g. G is a trigonometric function. Upward shift of 3. Nothing to it, no context. If I asked you for the average rate of change of g with respect to x on the closed interval from 0 to pi, could you do it? Sure, you can find the average rate of change of g on 0 to pi. Choose the difference quotient, g of pi minus g of 0 over pi minus 0. Plug in pi, plug in 0. As you can see, sine of pi is 0, sine of 0 is 0, 0 over pi is 0. Done. Bam. What if I ask you for the instantaneous rate of change of g with respect to x at x equals 0? Could you get that? Yes, by using the limit of the difference quotient. Now, what's our terminology? Have you gotten it yet? Basically, I'm asking you for the derivative of g at x equals 0. And this is how you read it. G prime of 0, or the derivative of g at 0, or dg dx when x equals 0, which again is the derivative of g when x is equal to 0. All right. The only last interpretation graphically, if you were to graph this function, which you know how to graph, would be g prime of 0 is the slope of g at 0. dg dx when x is equal is the slope of g at 0. All right, so we take the limit of this difference quotient. No problem. We can do this. G of x is given over here, so we should rewrite that. G of 0, just stick in 0. Sine of 0 is going to become 0. 3 minus 3. So you're left just with a limit as x approaches 0 of sine of x over x, which is going to, if you plugged in 0 here and here, you'd get an indeterminate form. So you'd think you'd have to do more work. But really, we've already done that work in the homework, so you don't have to do it ever again. You just kind of know that the limit as x approaches 0 of sine of x over x equals 1. You say, what was it that we did? This is what we did. We said that cosine of x is less than or equal to sine of x over x, which is less than or equal to 1. Okay? That happened, we looked at it between negative pi and pi. So if you graph this thing, 1 is this constant linear function. Cosine of x is going to look like this from negative pi to pi. And sine of x over x is kind of halfway in between, looking like this. Well, then we get to use what theorem? The squeeze theorem. That's right. So the limit as x approaches 0 of cosine of x is less than or equal to the limit as x approaches 0 of sine of x over x, which is less than or equal to the limit as x approaches 0 of 1. Well, what's the limit as x approaches 0 of cosine of x? 1. What's the limit as x approaches 0 of 1? 1. So clearly the limit as x approaches 0 of sine of x over x equals 1. Okay. There it is. Perfect. We're going to go over many notations for the derivative right now. And just like a pair of sharks, you need to eat it up.
No, cute. I'm gonna eat you too.
All right. So, let's make sure we got all our notations down for the derivative and various definitions we can use for the derivative. I'll explain that real quick. You have some function f. F of x, x goes in, f comes out. Fine. Or f of x comes out. If I ask you to take the derivative of f at x equals a, these are all equivalent statements. 1 through 5 are all equivalent. The derivative of f at x equals a is going to be equivalent to the slope of f at x equals a. In other words, if you graph that f function, its slope at x equals a, that's the derivative of f at a. If you were thinking of it in terms of a rate of change, the instantaneous rate of change of f with respect to x at x equals a. All equivalent statements. That's also the derivative of f at x equals a. This is Newton's notation, f prime of a. What does it mean? It means the derivative of f at x equals a. Leibniz notation, df dx. When x equals a, what does it mean? It means the derivative of f at x equals a. Okay, Got the notation. So how do we do the calculations again? Limit of a difference quotient. Difference quotient involves 2 points being driven infinitely close to each other. Now you're really familiar with this. F prime of A is equal to the limit as x approaches A of f of x minus f of A over x minus A. F of A is fixed in place. X f of x is driven infinitely close to A f of A using the limit as x approaches A. And you have 2 points where you could take a difference quotient. You know, you could take an average slope, but it's effectively an instantaneous slope, right? Because the points are effectively infinitely close to each other. They're effectively in the same spot is what I'm trying to get at. All right, here's an alternate definition that you also need to know for the derivative. And it looks different, but it's actually exactly the same. But it's also very popular. So f prime of A is also equal to the limit as h approaches 0. This is x approaches A. This is h approaches 0 of f of A plus h minus f of A over A plus h minus A. Notice the limit of a difference quotient. Here, x is approaching A, so this point, A f of A is, or x f of x approaching A f of A. Here, it says the limit as h approaches 0. H is approaching 0. What in the world is h? Well, it looks like it's a difference between A f of A and A plus h, comma, f of A plus h, right? So if we close that gap, the gap between these 2 points is effectively h, right? The difference between A and A plus h is h. If we close that gap, they'll bring the 2 points infinitely close to each other. The algebra works out better sometimes here, works out better sometimes here. That's why we have these 2 definitions. Graphically speaking, A f of A is this point right here. A f of A on this random f function I created. X f of x is this point right here. What are we doing in this first example? Well, we're moving x f of x infinitely close to A f of A. Taking a difference quotient and getting an instantaneous slope. Getting an instantaneous rate of change. Basically getting the derivative of x equals A. But what can we do instead? We could say, instead of viewing this as A f of A, we can view it as A f of A. Instead of viewing A plus h, instead of viewing x as, instead of viewing this point as x f of x, we can view it as A plus h, comma, f of A plus h. In which case, really, what's this distance between A and A plus h? H. We'll just send that to 0. What does that effectively do? Closes this gap, brings the 2 points together. Just to see it's the same definition. So, when you see this, the A plus h minus A, what's A minus A? 0 all the time. So you're always just left with an h in the denominator, like this. So it always reads this way. The limit as h approaches 0 of f of A plus h minus f of A over h. When you see it, don't think it's not a difference quotient. It is. It still has 2 points, A f of A and A plus h, f of A plus h, just like any other difference quotient. But the A minus A always cancels, so you're just left with h in the denominator. All right, you get it. This is the derivative of f at a point. The derivative of f at x equals a, and has many interpretations and multiple ways of expressing the limit of the difference quotient. All right, folks, try to get a hold of this. Man, if you're taking notes, you're just a champ. And I will be talking to you more about the derivative. Thank you, folks, for hanging in there. Really appreciate you.